Hello everyone, this is a brilliant question of the elastic collision. Here is a rod having mass m and length L and it is lying on a horizontal frictionless surface. Means we have to neglect the friction, there is no friction. It means we are going to conserve the linear momentum of the rod plus this particle system. So a particle of mass m is traveling along the surface and it hits at one end of the rod. The particle had the initial velocity u and the collision is elastic. After the collision, the question says the particle comes to rest, then we need to find the ratio small m by capital M. So basically, this rod is placed on a billiards table or on a snooker table. The table's surface is horizontal, but we will see the situation from the top. So for the solution purpose, let's draw the top view. We'll draw two diagrams, one just before collision and another just after collision. So here is the rod. It was lying here at rest. This diagram we are making just before collision. There is a particle of mass m which was approaching one end of the rod with speed u. The rod was at rest, rod had the mass capital M and the length L. Its mass is uniformly distributed. There is a point mass m approaching with speed u just before collision. Now we draw the diagram just after collision also. So here is one scenario just before collision and let me draw the diagram just after collision. Just after collision, this particle comes to rest. It means the scenario would be like this. M is at rest. It has no speed now. Just after collision, the rod's center of mass must be moving with speed v and the rod should get an angular speed omega also like this. Why like this? When this particle hits here, about the center of the rod you can sense how it is going to rotate. So the rod will spin like this. That's why we have taken omega in this sense. Now the surface is horizontal and frictionless. For the rod, the normal force and mg are getting balanced. There is no other force along the horizontal since surface is smooth. It means in the horizontal direction, we can conserve the linear momentum of this point mass and the rod system. So first of all, we will be conserving the linear momentum here. P initial vector is equal to P final vector. Initially, the linear momentum of this point mass is mu and the rod was at rest. This center of the rod is at rest. So capital M into 0. The final linear momentum we can write as mv plus small m into 0. This small m comes at rest and the rod's center of mass gets the velocity v in the forward direction. So from here, if you require, you get the value of v as mu by capital M. Save it for the further calculations. Now we are going to conserve the angular momentum also. Think logically, if this is the surface of the table and the rod is placed here, the point for angular momentum conservation we consider just below the center of mass of the rod and lying on the table. What I mean to say, if this was a table and let's say here is a point on the table, just above this point the center of mass of the rod is lying. Let's say the rod was lying like this. The center of mass of the rod was lying just above this point. Okay. Now the point on the table is at rest. And about this point on the table, if you check, the mg of the rod passes through this point on the table. The yellow point lies on the horizontal table. Mg of the rod passes through this point because the center of mass of the rod is just above that yellow point. So Mg goes there, and the normal force also passes through that yellow point. Means about that yellow point, the torque of the normal and Mg is already 0. About the yellow point, there is no friction force, so there is no torque of the frictional force. Now, about the yellow point, if you check, there is some impulsive force on the rod during the collision event, and the equal and opposite impulsive force will be acting on this point mass also. When the point mass hits the rod also applies equal and opposite force on the point mass. These forces are equal and opposite, so when you take that torque about this point, this yellow point which lies on the table, the torque of these two forces will also be 0. So basically about this yellow point there is no torque. Hence we can conserve the angular momentum of the rod plus particle system about that yellow point, which is lying just below the center of mass of the rod, and that yellow point lies on the table. So, writing the expression for the conservation of angular momentum, let me do that here. We write L initial is equal to L final. This is principle of the conservation of angular momentum, as the torque on the system was 0. Initial angular momentum, if we write about that yellow point, the line of action of motion of this point mass is here, and from here you can drop a perpendicular. This perpendicular has got a length L by 2. So the angular momentum of this point mass about that yellow point is L by 2 mu. Okay. Now the rod was at rest, so no angular momentum initially for the rod, is equal to L final. This point mass comes at rest, so no angular momentum for that point mass, and this rod spins with angular speed omega, so its angular momentum we will be writing as mL square by 12 omega. I center of mass into omega. You might remember that formula, L is equal to I omega from the rigid body dynamics. The rod is spinning about its center of mass, so we have taken I center of mass as mL square by 12, and rod's angular speed is omega. Agree with this? Now going further, this L can get cancelled out. This 2 and then 12 we can write here the 6. We have another relation here. We can write that omega is equal to mu 6 by ml. Do you agree with this? This omega is 6 mu by ml. Now another information lies in the question. The collision is elastic. We remember one thing, for elastic collision, the velocity of separation and the velocity of approach was equal along the line of impact. This is the line of impact, and along this line of impact, velocity of separation and velocity of approach must be same. So let us process that information here. Since collision is elastic, so velocity of separation and the velocity of approach along the line of impact must be equal. The velocity of separation we can easily find. This point, if we check, should have the speed v plus omega L by 2. The center of mass of the rod is moving with speed v. It means all the particles of this rod will have the linear speed v. Center of mass has the speed v, then this particle will go with speed v, this particle will go with speed v, this particle will go with speed v. Each particle of the rod will go with the same speed. If this rod's center of mass has the speed v, then this particle, this particle, this particle, each particle of the rod has the same speed v. Now comes the effect of the rotational motion. The rod has the angular speed omega like this. Due to this omega about an axis passing through the center of mass of the rod, here we can write the tangential speed as omega r, and this radius will be L by 2. So the speed here will be omega L by 2. So the end point of the rod at this bottom will have the speed V plus omega L by 2. Effect of this omega, if you want to show at the top, it would be in this direction, omega L by 2, because this length is also L by 2, and this point will get a tangential speed in this direction, omega into r, that r will be L by 2. So the velocity of separation, because this m mass came at rest, so this point of the rod is being separated at a rate v plus omega L by 2. And the velocity of approach, initially this point of the rod was at rest and this mass is approaching at a rate u. So velocity of approach is u. Agree with this? Now we are going to put the data. We have the value of omega, we have the value of v. We are going to put this data. Now we don't require this table, so I'm just deleting it. For calculation purpose, we require some space. V is equal to m small u by capital M plus L by 2, and that omega is 6 mu by capital ML. Agree with this? Is equal to u. Now we can see u is present in numerator in all the terms, so we are going to cancel out that u and u. Now we can cancel one L also here, L is present here, L is present here. Next calculation, this 2 and this 6 we can write here 3. Now we are left with what? Small m by capital M I am taking common. So here we are left with 1. Small m by capital M has been taken common. Here we are left with 3. And here in right hand side we have 1. I hope we are having the correct answer. This number is 4. Here is 1. So the small m by capital M can be written as 1 by 4. This is the absolutely correct answer. So here we are going to write the data as 1 by 4. I hope you enjoyed the solution. If you enjoyed it, please like this video, share it with your friends and kindly subscribe to this channel. If you have any doubt in this solution or in any other question, please post that in comment box. And which part of video you liked the most, kindly let me know in the comment box. Stay awesome and see you soon. Thank you.